I'll begin now. So today I'll talk about factoring as well as just finding roots of polynomials and applying that to solve some problems in math competitions. So first of all, let's just go over the definition of a polynomial. So a polynomial is a sum of several terms that contain different powers of the same variable. And throughout this presentation, I'll normally denote a polynomial as capital P of x, where x is the variable. So expressed mathematically, you would get this sort of form where P of x is equal to a sub n times x to the nth all the way to plus a sub 0, which is the constant term. And here you can see that P is a polynomial of the variable x, and there are various powers of x included in this polynomial. And we also specify that a sub n, or the leading coefficient of the polynomial, cannot be equal to 0. And in this case, the degree is equal to n. So let's also go over what a root of a polynomial is. Simply put, it's a value for which the given polynomial is equal to 0. So we can say this as P of r is equal to 0, where r is the root. And on a Cartesian plane or xy plane, the root represents the x-coordinate at which the polynomial intersects the x-axis. And also, one interesting property of roots is that, according to the fundamental theorem of algebra, all polynomials with degree n have n distinct roots, n non-distinct roots, which can be real or complex. And now let's move on to finding roots. So the simple way to do this is just to factor a polynomial using either long division or synthetic division. And you would get a polynomial that's in this form, where r1 all the way to rn are the roots. So let's also cover the rational root theorem. So suppose we have the standard form of a polynomial, as you can see here, and all the coefficients are integers, and the leading and the constant coefficients are both not equal to 0. And suppose that you have p and q, which are two integers, and they are coprime. Then if p of lowercase p over q is equal to 0, then this implies that lowercase p divides into a sub 0, and q divides into a sub n. And let's just go through an example of finding roots of a polynomial. So here we have this polynomial p of x is equal to 12x cubed minus 28x squared minus 9x plus 10. And so let's just try the really simple numbers first. So if you try plugging in 0, well, you're just going to get 10 because all the terms that contain x are going to cancel out to 0. So p of 0 is 10. And if you just try 1, this is the same as the sum of the coefficients, which will come out to be negative 15. And although it seems like this doesn't really help, if we plot these two on a Cartesian plane and we try to draw any sort of continuous line between them, we know that it must intersect the x-axis due to the intermediate value theorem. So essentially, from evaluating p of 0 and p of 1, we're able to deduce that there exists a root such that it's between 0 and 1. And motivated by the rational root theorem, we can try plugging in 1/2 for x, and actually this will produce 0. So this also implies that x minus 1/2 is a factor of the polynomial. So if you divide that out, then you would get this quadratic right here. And the quadratic is relatively easy to factor. You just express that, you take the 2 out first, then you express the negative 11x as negative 15x plus 4x, then you just get this product that you can see on the right. And if we further factor out 2 and 3, then you would get this, and it's much easier to see the roots. So the original polynomial is equal to this expression here, and then the roots are pretty easy to discern, and they are 1/2, negative 2/3, and 5/2. And you can also use this information about the roots to sketch a graph pretty easily, which I've done here. So moving on to the fundamental theorem of algebra, which I touched upon a few minutes ago, we can try to solve questions like this. So what is the maximum number of intersections that are possible between this cubic and the line y equals x? Well, first of all, let's just try to set them equal to each other to find the x-coordinates of the intersections. So we will get this equation here. And if we subtract x from both sides, then you would end up with this. And by the fundamental theorem of algebra, a cubic has 3 roots, and up to 3 are real roots. And in this case, it turns out that the two equations actually do intersect at 3 points, as we have predicted. So now let's also look at this example here. So p of x is a quadratic, and p of 2 is 4, p of 3 is 9, p of 4 is 16. Then we're asked to find p of x and also prove that it is a unique solution. So of course, it's pretty easy to see that p of x is equal to x squared, but how will we rigorously deduce this? Well, first, we define a new polynomial q of x, which is equal to p of x minus x squared. And since p of x is a quadratic, and you're subtracting another quadratic, the degree of q of x is at most 2. And furthermore, using the definition of q of x, we get that q of 2, q of 3, and q of 4 are all equal to 0. So there seems to be a contradiction here, which is that the degree of q is at most 2, but q of x has 3 roots. And the only way that this is possible is if q of x is equal to 0 for all values, as in it has infinite roots. So we deduce that q of x is equal to 0. Then plugging that in back to its definition, we have that 0 is equal to p of x minus x squared. And then if you just add x squared to both sides, you get this unique value of p of x, or unique polynomial that fits the criteria. So now let's apply these to some problems. So this one is from ARML a while back. So it states there exists a polynomial such that the degree of it is 1996, and p of x is equal to 1 over x for x is equal to 1, 2, and all the way to 1997, and the values are all integers. And we're tasked with finding p of 1998. So first of all, let's just express the given condition here, which is true for 1, 2, all the way to 1997. And the problem here is that this isn't a polynomial because we have a 1 over x term. So to solve that issue, we just multiply x to both sides. And then after subtracting 1 from both sides, you get this expression. We'll also define this to be equal to q, similar to what we did in the last exercise. So now we know that, just restating that, we know that this equals 0, or q of x equals 0 when x is 1, 2, and all the way to 1997. And this means that q of x can be factored as follows. C times x minus 1, x minus 2, and all the way to the last root. And the reason that the q is equal to a polynomial with degree of 1997 is that, by definition, it's x times p of x minus 1. And p of x has a degree of 1996. If you multiply that by x, then that's 1997. And hence, in the last line I show here, q has a degree of 1997. So now let's just try to solve for c. And the way we do that is by evaluating q of 0. So by definition, that's equal to 0 times q of 0 minus 1, but that's just 0 minus 1. So q of 0 is negative 1. And if we plug that into our factored form for q of 0, or sorry, q of x, then you get that negative 1 is equal to c times all of these numbers. Just isolating c by itself, you get that it is equal to 1 over 1997 factorial. So let's just rewrite that, or plug 1 over 1997 factorial in for c, and you get this expression for q of x. So now just to evaluate p of 1998, we just have to evaluate q of 1998. So let's just do that right now after restating the polynomial. You get that q of 1998 is equal to 1. And using the other definition for q, which is x times p of x minus 1, you get that 1 is equal to 1998, p of 1998 minus 1. Then just isolating p evaluated at 1998, you will get that is equal to 1 over 999. Now moving on to a second problem. This is an AME problem from a while back as well. And you see this really messy system of equations, and what we're asked to find is x squared plus y squared plus z squared plus w squared. So of course, since it's 4 equations with 4 variables, you could theoretically solve for them, but that would take a really long time and it would not be efficient at all. So there must be some sort of way to solve this with a more clever approach. So let's try to first condense all the information in these 4 equations into one, and I do that by rewriting that as follows. So we have x squared over a minus 1 squared plus y squared over a minus 3 squared, and you just add that all the way up to w squared over a minus 7 squared, and this is going to be equal to 1. And this is true for a is equal to 2 squared, 4 squared, 6 squared, and 8 squared. So just taking the example of a equals 2 squared, you can see how it matches with the first equation that you see here. And just rewriting all the numbers. So for instance, like substituting 3 squared with 9, then you can get this equation here. And what we're going to do is treat x squared, y squared, z squared, and w squared not as variables, but of the coefficients of a polynomial involving a. So right now, another problem we have is that a is in the denominator. So we need to multiply the top and, multiply both sides by the denominator. So you would get this rather messy expression. And this is all equal to 0 when a is 4, 16, 36, or 64. And you can see that the coefficient of the x to the 4th power term is -1 here, because the only a to the 4th power term appears in this last product, and it's multiplied by -1, so you just can deduce that the coefficient is -1. And recalling that the roots of this polynomial are 4, 16, 36, and 64, as I mentioned, you can write that in factor form like this. And of course, since the coefficients on the a to the 4th terms must match, you multiply the right-hand side by -1. And now you can see that x squared, y squared, and z squared and w squared are just coefficients of the a cubed term. And if you simply look at all of the a cubed terms of both sides, then you get this expression, or this equation. And just equating the coefficients on the left and right hand sides and subtracting both sides by 84, you'll get that x squared plus y squared plus z squared plus w squared is equal to 36. So yeah, these are two exercises that show how you can use the theorems I mentioned to solve problems. Thank you.